This is our second video lecture on section 9.5, and in this video we're going to be focusing on hypothesis tests for a population mean when the population standard deviation is given. In that case, you use the calculator function ZTest. Z because we're going to be using the normal distribution in order to get the p-value, test because it's a hypothesis test. We've laid out a 6-step procedure for a hypothesis test. Step 1 is to determine the hypotheses. Step 2, we identify the level of significance, which we denote by alpha. Step 3, we collect a sample and get some evidence from that, some statistics. Step 4, we compute the p-value. We compare that p-value to alpha to make the decision, and then we write a conclusion in plain language so that anyone could understand the results of our test. In the previous video, we talked about this from the perspective of testing a hypothesis about a proportion. This is a test for a mean, and so while the general steps are the same, some of the specifics will be a little bit different. For example, when we write up our hypotheses, we won't use the symbol p for our parameter because we're testing a mean. The symbol for a population mean is mu. So the null hypothesis will be the claim that mu equals some number, and we're going to use the notation mu sub 0 to represent our number. I'm choosing that strange notation because that's the notation you're going to see in your calculator. So the null hypothesis is still a statement of equality, but rather than saying that p equals some number, because this is a claim about a mean, we're going to write that mu equals some number. The alternative hypothesis will contradict that with an inequality. The alternative hypothesis will either say that mu is not equal to mu sub 0, that mu is less than mu sub 0, or that mu is greater than mu sub 0, and we'll have to read the claims in the problem to determine which one is appropriate. The principles are the same. The null hypothesis is a statement of equality. The alternative hypothesis is an inequality, but now we're doing this for means instead of proportions, so the notation looks different. Second step, you identify the level of significance alpha. This step will be done the same way. The value of alpha will be given somewhere in the problem, and we just have to find it. Step 3 is to collect the sample evidence. The evidence here will be different. We're not going to be counting up successes. In order to test a claim about a population mean, you're going to need a sample mean, which we denote by x bar. We'll also need the sample size, which we denote by n. And then the calculator requires one more input that doesn't come from the sample, and that's the population standard deviation. Notice that we're specifically looking at the case where the population standard deviation is known. The calculator is going to want to know that too. That will be another input that we have to put into the calculator. Because we're assuming that we know the population standard deviation, as long as we have a sample size of at least 30 or a population that's normally distributed, we can compute the p-value using the normal distribution. And so we'll be using a calculator function called ZTest to do that. We've learned enough about the normal distribution that we could calculate the p-value without using ZTest. We could just use normal CDF. But the ZTest calculator function is convenient, and so that's how we're going to approach these. Next, we make the decision, and the decision is made the same way for all of the scenarios, but I like to write it down anyway to remind you how it works. If the p-value is less than or equal to alpha, you reject the null hypothesis. And if the p-value is greater than alpha, then you fail to reject the null hypothesis. When we say that we're rejecting the null hypothesis, we're saying that we're pretty sure the null hypothesis is false. We do that when the p-value is small. And we consider a p-value to be small if it's smaller than the alpha that we found in step 2, smaller than the probability of a type 1 error. So if the p-value is less than alpha, reject. I've suggested that you remember that by the mnemonic PILTAR. P is less than alpha, reject. If the p-value is greater than alpha, then the null hypothesis is too believable for us to reject it, so we say that we fail to reject it. Now the decision comes in a nerdy language, reject HO, fail to reject HO. Somebody who hasn't learned any statistics would have no idea what that means. So we're going to end each problem by writing an interpretation, a conclusion, and it will address the claim that's made in the problem in a much more simplified language so that it would be easier to understand what the result of our test is. I think we're ready to jump into an example. You'll notice that these read a little bit differently because they're about means and not proportions, but the principles are the same. The basic idea is the same. Here's our first example. In a large supermarket, the customer's waiting times to check out are normally distributed with sigma equals 2.5 minutes. A random sample of 24 waiting times produced a mean of 11.6 minutes. Does this sample provide sufficient evidence to support the claim that the mean checkout time for all customers exceeds 10 minutes, use alpha equals 0.01. So we have a 1% significance level there at the end. So here's the basic idea. The store is worried that the customer's waiting time is getting too long. They're worried that it might be longer than 10 minutes on the average. So they take a random sample of 24 waiting times, and the mean of those waiting times was 11.6 minutes, which is obviously bigger than 10. But is that difference of 1.6 minutes statistically significant enough to take the leap that the mean of all customer waiting times is more than 10 minutes, given that we have such a small sample size and a standard deviation of 2.5 minutes? That's what the test is about. Can we use the sample to make an inference about the entire population? This is a hypothesis test, and you can tell because we're being asked whether or not we can support a claim. This claim is about a mean, not a proportion. So when we go to our first step to determine the hypotheses, the null hypothesis and the alternative hypothesis will deal with claims about mu, not p. Let's go back to the problem and see if we can identify the claim. We're being asked if we can support the claim that the mean checkout time for all customers exceeds 10 minutes, which means that it would be greater than 10 minutes. As we've discussed before, it's the alternative hypothesis that takes the inequality symbols. So the alternative hypothesis would be that mu is greater than 10. The null hypothesis uses the same parameter and the same number, but it's an equation. It's a statement of equality. So the null hypothesis is the claim that the mean waiting time is exactly 10 minutes, and the alternative hypothesis is the claim in the problem, which is that the mean is greater than 10 minutes, exceeds 10 minutes. The second thing I ask you to do is identify the level of significance alpha, and that's easy to do here because it's explicitly stated at the bottom. Use alpha equals 1%, 0.01. Step 3 is to collect the sample evidence. We were told that a random sample of 24 waiting times produced a mean of 11.6 minutes. So the sample mean is 11.6. The sample size is 24. And there's one more input that the calculator is going to want. While it's technically not sample data, the calculator is going to want to know the standard deviation. And we noticed that we were given the population standard deviation of 2.5 minutes. So sigma is 2.5. If you're curious why I jammed that up at the top, it's because this is the order that the calculator function is going to ask for these inputs, sigma, then x bar, then n. But it really doesn't matter what order you write these in as long as you type them in the correct order. That 24 is a little too small for the central limit theorem, but we don't need the central limit theorem here because we were told that the customer's waiting times are normally distributed. The calculator function we're going to run to get the p-value, which is step 4, compute the p-value, is called ZTest. To access ZTest, you press Stat, scroll to Tests, and it's the very first option. ZTest is choice 1, so you can hit Enter or the 1 key. You want to make sure you're in Stats mode because we don't have a set of raw data. Mu sub 0, that's why I use that nerdy notation in my description up here. Mu sub 0 is the number in the hypotheses. We're comparing the mean to 10 in our hypotheses, so mu sub 0 is 10. Again, I jammed sigma in here because it asks for sigma before it asks for x bar and n. Sigma is 2.5, x bar is 11.6, n is 24. This last choice of input wants to know the symbol in the alternative hypothesis. The claim was that the mean exceeds 10 minutes, which is a greater than claim. So we want to choose the greater than symbol, which is the last option. So this line now says mu is greater than 10. You'll actually see that on the output screen. First line is the name of the test. This is becoming more and more important. We're now up to 5 different calculator functions, so make sure you use the right calculator function. Second line should match your alternative hypothesis, and here it matches it symbol for symbol. Mu is greater than 10. The third line is called the test statistic, and if we were doing this by another method, we'd need that. We're using what's called a p-value approach, so it's the next line that we need. And we see that p equals 8.58. No. But that is not a p-value of 8.58. A p-value is a probability. Probabilities can't be bigger than 1. So what's going on? This is in scientific notation. This isn't a large probability. It's a very, very small probability. That -4 is telling you to move that decimal point 4 places to the left. Our p-value is approximately 0.00086. This is a very small probability. What this p-value tells us is if the null hypothesis was true, and if the population standard deviation was 2.5, and if we assume the sample means are normally distributed, then the probability that we could have gotten a sample mean of 11.6 or more from a sample of size 24 is around 0.00086. So if we round that up to 0.001, that's like a 1 in 1,000 chance. It would be very, very unlikely that we would get a sample like this if the null hypothesis was true. So we don't believe the null hypothesis. The null hypothesis is almost certainly false. Now, we don't have to reason through it like that in our class because we have a rule. We compare the p-value to alpha, and if the p-value is less than or equal to alpha, we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. We say we fail to reject it. Well, 0.00086 is definitely smaller than 0.01, and since the p-value is less than alpha, we're going to reject the null hypothesis. We're quite sure that the null hypothesis is false, and so we reject it. When we reject the null hypothesis, we are going to replace that claim with the alternative claim. We're rejecting the null hypothesis in favor of the alternative hypothesis. These interpretations are written very similarly to how we write the interpretations for the one-prop z-test, except you just have to remember that we're talking about a mean here and not a proportion. So I'm going to start here by writing there is enough evidence. I'm often asked how to keep straight when there is enough evidence and when there's not enough evidence. When you reject the null hypothesis, it's because you're pretty sure you have enough evidence to do so. So you had enough evidence to reject, therefore you have enough evidence to support the alternative. So there is enough evidence to support the claim, and this is where I go back to the problem and look at the claim. The claim was that the mean checkout time for all customers exceeds 10 minutes. You could take a little poetic license here and say there is sufficient evidence or there is statistically significant evidence. You don't have to use the word support, you could use some synonym there. You do have to make sure that you say it's the mean or the average checkout time. Without the word mean, this statement is false. If we just say there's enough evidence to support the claim that the checkout time for all customers exceeds 10 minutes, that's false. We don't have evidence to suggest that every single customer needs more than 10 minutes to check out. We're saying that we're pretty sure that the mean checkout time exceeds 10 minutes. So while you can alter some parts of that, including the parameters, absolutely essential. Including the variable is absolutely essential, the checkout time. The population matters. So based on our sample evidence, we got a really small p-value. That p-value tells us that the null hypothesis is not very believable, so we rejected it, and we replaced it with the alternative claim. We're going to support the alternative hypothesis because we're pretty sure the null hypothesis is false. Let's try another example. The owner of a jewelry store believes that people are spending less on engagement rings than in the previous year, when the average was $5,600. A random sample of 36 engagement ring sales has a mean expenditure of $5,367. We can assume based on historical data that the population standard deviation is $1,400. Use a 0.10 significance level to test the jeweler's claim. Now, in this example, we have to put a little more together than in previous examples. Now that we've got some experience, I've written this one in a slightly less direct way. We're going to have to put some thought into this to get the 6 steps completed. But you can tell it's a hypothesis test. We're being asked to test the jeweler's claim. Step 1 in a hypothesis test is to determine the hypotheses. We need a null hypothesis and an alternative hypothesis. Unlike previous examples, we can't just go to the last sentence to get the claim because all it says is test the jeweler's claim. So now we have to go seeking through the problem to see what the jeweler's claim is. The owner of the jewelry store believes that people are spending less on engagement rings than the previous year. And in the previous year, the average was $5,600. So piecing that together, the owner is guessing that the mean is now less than $5,600. That's the alternative hypothesis because it's an inequality. The null hypothesis would be the claim that the mean is the same as the previous year, that the mean is still $5,600. So the null hypothesis says nothing has changed from the previous year. The alternative hypothesis says that the average is lower than it was in the previous year. Took us a little more work to get there, but same idea. Step 2 is to find alpha. And here we didn't use the symbol sigma, but it says 0.10 significance level. So alpha is 0.10. Step 3, find the sample evidence. There was a random sample of 36 engagement ring sales, and the mean was $5,367. That is big enough to satisfy the central limit theorem, so we don't need to worry about whether or not the population is normally distributed. We will need another piece of evidence for the calculator, and that is the standard deviation. We're told to assume based on historical data that the population standard deviation is 1400. Because the calculator will ask for sigma before the sample data, I'm going to stack it on top. So again, to spell out what we're doing, obviously $5,367 is less than $5,600. It's over $200 less. That seems like a wide gap. But is that difference statistically significant considering our sample size and our standard deviation? Can we extrapolate from this that the mean expenditure on all engagement rings is now less than $5,600? Or another way to say that is, can we conclude that the mean expenditure on engagement rings will be less than it was in the previous year? This is where the calculator comes in. And I mentioned this at the beginning of the video. We could actually do this with normal CDF. We don't need ZTest. But ZTest is so convenient, so we're going to do it that way. Stat, scroll to tests. ZTest is choice 1. mu sub 0 is the number in the hypotheses, which is the mean from the previous year, $5,600. Sigma is $1,400. X bar is 5,367. N is 36, large enough to satisfy the central limit theorem. And the claim is that the mean has been reduced from the previous year. That is, that the mean is less than $5,600. So we choose the less than symbol. So the calculator is going to tell us the probability that we could get a sample mean of 5,367 or less if the null hypothesis was true. It's going to use a normal distribution to do that because that's what ZTest uses, and we know a normal distribution is appropriate because the sample size is greater than or equal to 30. We're using the central limit theorem there. Calculator does that in a blink when you hit calculate. First line is the name of the calculator function. Second line should match your alternative hypothesis. Third line is the test statistic. It's that fourth line that we're after, the p-value. The p-value is around 0.16. So the p-value is telling us that if the null hypothesis was true, the probability that we could have gathered a sample of 36 engagement rings with a mean cost of $5,367 or less is around 16%. That's around 1/6. That would not be an unusual event. Something that happens 1/6 of the time isn't rare. So that means that the null hypothesis is plausible. So based on intuition, we wouldn't want to reject the null hypothesis. You guys don't have to use intuition though. We have a rule. If the p-value is greater than alpha, then you can't reject the null hypothesis. So we're going to fail to reject the null hypothesis. We do not have enough evidence to show that the null hypothesis is false. The null hypothesis is believable here. That doesn't mean we think the null hypothesis is true. So when we write our conclusion, we're not going to say that we're supporting the null hypothesis. That's not how that works. The evidence, in fact, leans towards the alternative hypothesis being true. It's just not strong enough for us to be sure. And so we're not going to go out on a limb and support the alternative hypothesis. We're going to say that there was not enough evidence to support the alternative. I get to this point, there's not enough evidence to support the claim, and then I go back to the problem to see what the claim was. And the claim is that the expenditure is less than it was in a previous year. You have to remember that we're testing a claim about a mean, though. So it's the claim that the mean expenditure on engagement rings is less than $5,600. In other words, this sample does not provide enough evidence for us to be sure that the average expenditure on engagement rings is less than it was last year. One more. This is that classic example that I talked about in the past. This study has been done many times. I picked one specific instance of it with a small sample size. It says a random sample of 15 healthy adults yields a mean body temperature of 98.2 degrees Fahrenheit. Assume the distribution of body temperatures for healthy adults is normally distributed with sigma equals 0.62 degrees Fahrenheit. Test the claim that the mean body temperature of healthy adults is different than 98.6 degrees Fahrenheit. Use 0.05 as your significance level. Let's run a hypothesis test. All right, we're testing this claim. So step 1, write down the hypotheses. The claim stated at the end of the problem is that the mean body temperature is different than 98.6. So when it says different and doesn't specify, that would be not equal to 98.6. You could be excused for using the symbol less than because the sample data points in that direction. I tend to take the claim literally, and when it says different, I test that specific claim. Different would be not equal to. But I could see why you might choose less than here because the sample data points in that direction. The null hypothesis is the standard belief that the mean is equal to 98.6. While it's natural for that to be the null hypothesis because we're kind of testing the status quo, I don't need to think of it that way. I know the parameter has to be the same, I know the number has to be the same, and I know it has to be an equation, so I can construct the null hypothesis from the alternative hypothesis. But remember, the point is to test this standard belief that the average healthy body temperature is 98.6 degrees Fahrenheit. So we have our hypotheses. Step 2 is identify the level of significance, which we denote by alpha. The last sentence tells us to use 0.05 as our significance level. This is the most common value of alpha. Step 3, collect the evidence. We've done enough of these now that we're going to look for the standard deviation first. The standard deviation comes from the entire population. That's why we're going to use ZTest on this one. Sigma is 0.62. The sample mean was 98.2. The sample size was 15, which looks small, but we were told to assume that the distribution is normally distributed, so we're okay there. And now we're ready to calculate the p-value. Stat, scroll to tests, choice 1. Mu sub 0 is the number in the claim, which is 98.6. Sigma is 62 hundredths. X bar is 98.2. N is 15. And we're choosing the not equal to symbol here because we were asked to test the claim that the mean is different than 98.6 without specifying a particular direction, less than or greater than. We calculate. First you see the name of the test, then you see the alternative hypothesis, the test statistic, which we ignore, and then the p-value, which is around 0.012. That p-value is telling us that if the null hypothesis was true and the average healthy body temperature really was 98.6, then the likelihood that we could have gathered a sample of 15 healthy individuals with a mean body temperature of 98.2 degrees would only be around 1%. It wouldn't be very common. Now that's not ultra rare either, but it wouldn't be very likely. Only 1 out of every 100 samples of size 15 would give us a sample mean that far away from 98.6. Is that small enough to reject? Yes, because of the value of alpha, right? We're using the standard value of 5%. But if for some reason we decided to test the claim at a 1% level of significance, then we couldn't reject. And this is where some of the objections to hypothesis testing come in. At the 5% level of significance, we're comfortable saying that the null hypothesis is false. At the 1% level of significance, we would not be. This is why you often see people just publish their p-value and leave it up to the reader to determine whether or not that's statistically significant. But if we go with the standard value of alpha of 5%, we would reject the null hypothesis. The p-value is less than 5%. And if we reject the null hypothesis, then we're going to support the alternative hypothesis, which is the claim that the mean is not equal to 98.6. To address the issue that the value of alpha matters, what a lot of textbooks will teach is that you should include the significance level in your sentence. So you would say something like, there is enough evidence at the 0.05 significance level to support the claim, kind of admitting that your decision was based on that choice of alpha. I don't like to include the significance level in my interpretation because I'm trying to keep my interpretation understandable. So now we've gone through 3 examples of testing a claim about a population mean when the population standard deviation is known. You can see that the procedure is similar to what we talked about for proportions, but it does require a little bit of different wording and you need different evidence. If you're having trouble keeping any of that straight or just need some clarification on something, let me know.